So let me recognize our second keynote speaker, Behruz Omidvar-Tehrani, for his tremendous effort to join us in order to share and exchange with us on one of his topic of interest. So Behruz, as Genova said in the beginning of the program of the workshop, is a research scientist with a focus on interactive data systems. He has held position actually in Naval Labs Europe, the Grenoble Alpes University, and the OU State University. So actually his research interest is in the area of data management and at the crossroad of data mining databases and machine learning. And today he will talk about enabling interactivity between human and artificial intelligence. And let me say the floor is yours, Behrouz, and we are waiting for your interesting talk. And then we will have some questions.
Sure. Thank you very much. Thank you, Shireen, Genevieve, and Nadia for the invitation. Okay, so let's dive in. So I'm going to talk about today about this term interactivity. And we've heard this word before, maybe in human-computer interaction, but here I'm going to look at it from a different angle, which is interactions between users and artificial intelligence. And more specifically, I'll elaborate on that later in the slides, that by artificial intelligence, I consider more, I mean a data system that we'll see what it means. Okay, let's see first the context of what we're talking about here and what do we mean by this interaction and what is missing here really. So the context here is information seeking. And it simply means that we are considering scenarios where users in different roles want to get some information from a data system where some data is stored, structured, unstructured, semi-structured, and there's a task, there is an information seeking task to be fulfilled. And usually there are different paradigms which encapsulate this notion of information seeking. It is either a search or recommendation, which is a search without a query basically, or exploration, which is a search by experience or searching iteratively basically. And then have, you know, users go through these different information seeking tasks in their different roles. They can be data owners or domain experts. They know what they want, but they don't know how to ask questions about that. They could be data scientists who they have enough tools to make questions, but they don't really know what are the good questions. And they can be simply information consumers, like someone who wants to buy a good camera online in Amazon. And again, there is a task of information seeking in this case as well. Now, um, the main goal in information seeking, if we want to really have an ideal, a full-fledged information seeking, it turns out that such system should enable users to interact with their data system in a in an effective way, because with these interactions, then they are able to fulfill whatever tasks they had in hand. What are the examples of this task? For example, in the case of a domain expert, in our case, a medical expert, the task of information seeking could be to explore the effect of air pollution in some regions on the chronic respiratory diseases. Or in case of a data scientist, the task of information seeking could be to explore the banking data to find patterns and trends in loan records, for example, to find what was a good loan or what is a bad loan based on the characteristics of the users who got those loans. And also for an information consumer, as we said before, an information seeking task could be to buy, for example, a good point and shoot camera at Amazon or any other online shopping platform. Um, okay, now that the notion of information seeking is clear for us, let's see how does it usually happen in the state of the art. So usually we have this kind of a machine learning pipeline where we start from data collection and data cleaning, and then we go through components such as data mining or machine learning, prediction, description, and all this. And we end up with data presentation or data visualization so that we can see, um, we can visualize, and we can comprehend the information that we were seeking, right? So for example, here I'm showing an example of Tableau, which is a famous off-the-shelf tool for visual analytics. Now, the question is that, okay, now that we have this pipeline and we have basically several of them, are we good? Is information seeking considered to be a solved problem? Well, there is a small problem here, which makes information seeking still a challenge and an open problem. And the challenge here is that when we are thinking about this notion of a task and information seeking, we usually have two groups of tasks, subjective and objective tasks. Um, in a seminal paper in last year VLDB conference called Subjective Databases, um, um, researchers from Megagon Labs, um, uh, you know, really pictured this notion of subjectivity and how this notion of subjectivity makes decisions and decision making harder for end users. So just as an example to clarify between objectivity and subjectivity in information seeking, let's imagine in a very simple querying scenario that there is a user who wants to receive a list of hotels with some criteria that she has in mind, right? You want to receive this list, for example, in booking.com or in Airbnb or whatever, to finally pick one. And then here we can consider that this constraint, which is in the mind of the user, could be defined objectively or subjectively. For example, the user could say that, well, I want to have hotels whose price is lower than $300 per night. With this information about the task, we can simply form a SQL query and we're done. We can serve the user task, and that's good. But the problem is that most often the task in our minds as end users is subjective, where the same question is basically like that I want to receive hotels where their price is reasonable. What does it mean reasonable? The system has no knowledge about that. What does it mean reasonable for the user? Even maybe the user herself doesn't know what reasonable mean for her, and she just want to see how hotels cost in general, so that she comes up with a notion of reasonability, for example, in this case. So um, the challenge of subjectivity makes information seeking a bit challenging. And usually this subjectivity comes from two types of users. One we call complex users, and the other one we call cold users. They are terms usually used in recommendation state of the art, but it can be also generalized to other domains. Complex users are the ones, as we had the example of listing hotels, are the users who don't have really a clear or objective task in their mind. And this is most of the time the case of end users. They want something, they know that they want to buy a good camera, they want to they want to have a very good insight about their data, but they are not really sure what it is and how they should specify that. And on the other hand, we have also cold users, where um, they are the ones who have either intentionally chosen to not share any information with the system because of privacy concerns or whatever, or there is no information about them. They are just newcomers to the system. Again, in this case, even if the user wants to guess what is the clear message behind their subjectivity, again, it is not possible because we have no knowledge about the user. So usually with complex and cold users, we have this problem of subjectivity. So in the examples that we had before, the subjectivity can be like this. In the case of our medical expert, well, we know that she's seeking about some effects, some interesting effects. But now the question is that how is this interestingness of effects defined? Or in the case of the data scientist for patterns and trends in loan records, again the question is that what does distinguish between an interesting and uninteresting pattern or trend? And in case of the information consumer, again the question is that what is a good camera for the user to buy? And of course, the obvious question here to ask is that, okay, now that we're dealing with such kind of subjective tasks and information seeking, how can we obviate those? Um, and researchers here have two different ideologies. The most famous one is Ben Schneiderman in the domain of visual analytics and visualization, believes that if someone doesn't have a clear question in mind, she shouldn't come to data systems. She should decide to ask a question from the system whenever it is clear. Okay, it's easy to remove the question, but maybe another strategy is to really see if we can do something with this subjectivity and still try to serve the user. So the idea that I want to promote here is that, first of all, we have to acknowledge that no scientific method, either in databases or data mining and machine learning, can provide a precise answer for a subjective task, because this notion of reasonability, for example, is not a clear term for anyone, neither the system nor the user. However, what we can do is that we can come up with a frame of reference or some sort of a range that maybe the needs of the user just fall into that range. This is something that seems possible. There is a notion of Fermi estimation in the state of the art, which is an approach to basically find this frame of references for questions such as that. There are typical questions mentioned for Fermi estimation, like how many piano tuners exist in Chicago, or how many civilizations exist in the whole Milky Way galaxy, which is called Drake equation here, right? So the way that Enrico Fermi, the Italian physicist, proposes to solve these questions, which we don't really have an exact answer for that, is to iterate with some supervisor or someone who has a better knowledge about that, and then basically either we overestimate or underestimate the real answer or the precise answers. And um, uh, gradually in these interactions, overestimates and underestimates will cancel each other out, and hopefully by the end of the process, or with enough iterations between the user and that supervisor, uh, we can hope that we get more accuracy from the beginning, or we can obtain that frame of reference that we set. Following the example that we had, it is something like that again the user starts with this question that, hey, I want a hotels with reasonable prices, and the AI agent just makes a rough guess that, okay, so maybe being reasonable for you means a price range between $50 and $100. Now the user has something to play with, and now the user can say that if it is an overestimation or an underestimation. In this case, she says that it's an underestimation, I can go for more. And then now the AI agent has a better knowledge about what reasonability could mean for the user. Now there's another suggestion saying that, okay, now what about $500 to $700 per night? And now the user say, no, it's an overestimation. And now maybe somewhere in the middle should be the answer. So the AI agent provides something around 200 or 300. And then the user says that, yes, should be okay for me to consider that as being reasonable, right? So it seems that this kind of interactions could be it could be a solution to subjectivity. But On the other side of the extreme, we have this objective task. Just for inspiration, let's see how traditionally in the literature we solve simple objective tasks. What if our tasks were simply objective? What would we do for them? And basically, in the case of objective task, our task is easy because we have several solutions developed for them in data mining, databases, machine learning, and visual analytics for fulfilling these clear tasks. For example, again, coming back to our examples, for the medical expert, we can have a statistical and visual analytics methods such as Kaplan-Meier charts to, obtain a question which has been turned out to be a clear task. For example, now the medical expert wants to compare the survival rate in the high and low air polluted areas. Very clear question. Or if the question of the data scientist was, again, a very clear question, for example, find the correlation between the loan approval and the investors' demographics, again, linear regression could be easily the answer, or, other cases similarly. So for an objective task, it is simple. As we said before, we build an AI system or a machine learning pipeline with components of machine learning, from data cleaning or data preparation to data presentation, and passing the task through this pipeline, we can obtain our task easily. But of course, using these end-to-end machine learning pipelines that we had before, so we have problems concerning subjective task. Of course, we don't have any user feedback incorporated in the system, so the user has no choice in the decision-making process. The context of the user is not considered because user is out of the loop, and also there is no kind of transparency in the system. So a recommender system recommends something, and we have to accept that this was a good recommendation. There is no other way for the user to understand why I have received these recommendations. I won't talk about transparency and personalization challenges here, but my focus, as the title of the talk suggests as well, it would be on user feedback and interactivity in this case. So now the takeaways from the solution, like somehow a scheme of a solution that we provided for subjectivity using Fermi estimation, and also the takeaway from how we are already doing things in objective task with machine learning pipelines. If we combine these two takeaways, we can say that, okay, inspired from Fermi estimation, we can incorporate interactivity between human and um, artificial intelligence in AI pipelines to come up with a solution for subjective information seeking tasks. So this was some sort of a long introduction about, a rough idea about how subjectivity can be handled in information seeking. In the rest of the talk, depending on how much time we can have, I will talk about these two big questions. One is that now that we want to have these interactions, how can we formalize these interactions? And once we have formalized those interactions, then the next question is that let's go one step further and ask ourselves if we can learn those interactions, if we can have some sort of a super AI agent who can look at the interactions between user and a data system and imitate the user so that the user would have less interaction to do in future iterations. Let's see how we can answer these two questions. Um, I start with the first part about formalizing interactions and how this can be done in a typical AI system. Here I want to point out to Moravec's paradox, which is a simple paradox behind most of our assumptions in data systems and artificial intelligence, where the expertise of machines and users does not necessarily overlap, and they have strength in different places. And this is a good motivation for these interactions to come up with a system like what I'm depicting in this slide, where we have an AI agent as an ML component in the pipeline, for example, here, and we have the user. Remember that before, this user was sitting outside the loop, but now she's interacting with each single ML component. And by interaction, I mean two different types of interactions. One arrow starting from the users, ending on the AI agent side, which I call feedback, and the reverse one, which I call guide. Um, the first one simply means that now the user is able to provide what she wants or what she thinks to the system, simply like these likes and dislikes that we can consider in a system. That, okay, what I received was good, but maybe I want to see more in this dimension or something like this. And based on this feedback that the system receives, it can get smarter, it can get more personalized, and then it can guide the user by providing results which align more with what the user wants. And again, iteratively, the user with this new guidance will provide a wiser feedback. And this goes on and goes on, and hopefully we will, both the AI agent and the user will converge to the task, the subjective task that the user wanted to fulfill. And I call the whole loop of feedback and guidance exploration in this case. And the whole system where users are inside the system, I call them mixed initiative systems. So in a mixed initiative system, turns out that there is like a conversation between the user and the AI agent. As we said before, the system guides the user in the plethora of data points, and the user provides feedback on how this guidance should be performed. And as depicted in this figure, um, in such system, in mixed initiative systems, both the user and the agent will grow together, will have a better understanding of the other side, so that they can converge on the target. So it seems that the user with these loops of guidance and feedback will go towards clarifying the subjective task that she had in mind, and also the AI agent will go towards understanding the user needs better. So just a quick example to show how these dialogues can happen in a real scenario, in a real world case. So let's assume that there is a program committee chair, a PC chair, and she's tasked to build a PC for a conference, for a workshop or whatever. Um, and the task is, of course, an example of a subjective task, because the PC, we have some ideas about how the PC should be built. It should be geographically distributed. The male and female researchers should be balanced. Their seniority levels and dexterity levels should also be balanced. So we have some rough ideas, but we cannot really quantify these ideas at first. So what happens is that we have this notion of mixed initiative systems. The user starts exploring some, subset of researchers labeled with some commonalities. For example, we have 46 researchers who are junior and published a lot of publications, and other kind of groups. Then by looking at these groups, now the user can provide a wiser feedback, because now she knows how researchers are defined in this data set. What do we know about the researchers? How can I choose researchers better for my PC? Then, for example, the PC chair says that, okay, this group of researchers who are prolific, publish a lot of publications, and they have at least one publication in SIGMOD, they are a good candidate. So this is my feedback. I want to see more about these people. So she asks the system in terms of a feedback that I want to explore more about this group. And then in the second iteration, this is the system which guides the user by providing more groups of researchers similar to what she had already seen. And this process will go on and go on until converging on the task, which is forming the program committee. So I just wanted to show how this looks like in practice, this conversation that we talk about. Now, we want to know what is this feedback and how can we model this feedback. So basically, the way that we see these feedbacks in a mixed initiative system is modeled by exploration actions. And it simply means a function called explore DKE, where D is an input data cube, and data cube in OLAP terminology simply means a subset of data in our case. And we also pick one type of exploration action, which I introduce in the next slide what they are. And then by running this function explore DKE, I will obtain K other cubes as guidance called big D, which are relevant to my input small d that I had before. Like in the example that we had before in iteration T, we had one input group. We wanted, we were interested in that group. And so it was our feedback D. Then we chose an exploration action. And with that, we obtained, some other groups as big D. Here we consider K equal to 3. And this is how the process of exploration actions work. And with different user studies and considering different cases, looking at different papers proposing different forms of um, um, explorations, we have different examples of exploration actions. For example, explore around means that, hey, you have to the output group should have some similarity with the input group, but at the same time, they themselves should maximize diversity, so to provide different directions in the exploration for the user. We have other exploration semantics as well. For example, we can say that by distribution, exploration means that first, we want to have some relevance between the input group and the output data cubes or output groups. For example, with Earth movers distance in this case, on their score distributions, if there's a score associated to each group. And at the same time, we want to also maximize the diversity in the final group. So this is basically the different examples of these um, exploration actions. I won't go into the details, but basically one example of that, like explore around, as we said before, should satisfy some local constraint, which is in this case the Jacquard with a given threshold, and also should satisfy a global constraint, which is in this case the diversity. And then by formalizing interaction in this way, and also applying exploration actions to a real scenario, such as forming the program committee that we observed before, we can have results such as this one. This is the result of one of our studies that we made, and we see that for different for forming different PCs, SIGMOD, VLDB, SIGChem, and also WebDB Workshop, for reaching 50% of the PC population and also reaching 80%. In average, we can reach 50% of the population in less than 10 steps. So this means that this way of formalizing interactions potentially work. But does it mean that it's enough? Well, let's move quickly to the second part of the talk and see what we can do on top of these exploration actions. Now, as we said before, what we are up to now is that we've enabled the user to have basically a toolbox of different exploration actions. She can pick one of them, and with that, she can navigate in the data. She can pick another one and navigate again in the data. And hopefully, by the end of this exploration session, she can find a subset of data in which she's interested. So this is what we did right now, and it showed that it has some real applications in real scenarios. Now we have another question in mind that, okay, it seems that there is some sort of a burden on the user in this kind of mixed initiative systems, because at each iteration, the user has to stop, provide the feedback, and go on. Again, stop, provide the feedback, and go on. Now our question is that with all the developments that we had in machine learning and artificial intelligence, can we make our AI agent a bit more smarter so that the AI agent can help, can assist the user more, so that the user has less to reach a target that she's seeking. Okay, so on the paper, ideally it is interesting to do so, to be able to do that. But what is a challenge in performing that? Um, I want to cite Robin Hoggart, who is a professor at the University of Barcelona here, that usually when we talk about learning, um, we talk about learning in kind environment. So he's talking about two different environments, kind and wicked. And what is important is that usually in all, or let's say most of machine learning applications that we consider, we are dealing with kind environments, or another simpler word for that is closed word environments, where the environment can be defined with a set of rules, and that's it, right? And then once the agent can learn all those rules and relations between those rules, which make tactics, um, then the AI agent can basically perform at human level or better than human level, which is the case of, for example, chess. We know the development of AlphaGo, for example, or even games, sport games such as tennis or golf, where practice can make a grandmaster in those domains. And ML systems are very good to imitate kind environments in this case. But there is another kind of environments which has received less attention in machine learning because they are more difficult to imitate, which are open board environments, environment where the rules change. The rules of the chess never change. They always stay the same. But in some domains, for example, share investment analysis, even an expert may get surprised by what happens tomorrow morning. I mean, there is always this kind of serendipity, or this randomness, which is in the an open world situation. And there it seems that humans are more successful in open world environments, in learning open world environments, by learning strategies rather than techniques, where strategies uh, may be in line with tactics, but also maybe they don't overlap with tactics, and um, they talk about a different thing. Um, the problem with wicked environments is that ML systems cannot really perform well there. And the big reason there is that we don't have a lot of logs there. And even if we have logs in such wicked environments, because the whole story is not about learning patterns or trends, the learning process would be a bit harder than we think. And information seeking, which is the central problem that we are talking about today, often occurs in a wicked environment, in an environment where variables change in time. Okay, so with this knowledge that we have, that at least we know that um, information seeking happens in a wicked environment and it is challenging to learn these interactions, let's see what we can do. First of all, we can formalize the environment and see how it looks like. We can consider in some sort of a reinforcement learning structure or terminology. We can consider exploration states. We can say that in whatever scenario or moment that the user is interacting with the AI system, there's a state that the user is sitting on. And the exploration state is denoted as a tuple small d and big D, where the small d is the input and the big D is the output, basically. So simply the state shows that you are at this moment, it was the feedback that you provided, and by this feedback, the AI system gave you the guidance such as this one. And this tuple makes one state. And then the sequence of these exploration states make an exploration session, where by the tuple S and En, we hope that we will have we will reach the target, the user reaches the target. And here to capture this notion of a strategy that we discussed before, we define this notion of a policy, which is a known notion in reinforcement learning, where it is simply a mapper function between states and actions. So ideally, if we find the optimal policy, the idea is that whenever we provide a state to the system can tell us what is the optimal action to take to reach to a target. So basically, as the picture depicts here, is that the user starts with a suboptimal policy, and at some point she wonders what should be the next action to apply. And if there is an agent with an optimal policy, she can takes over here and says that, hey, this is the optimal action that you should take. And then again, by this kind of mixed initiativeness that we discussed before, we can reach to target. Now the question is that what is an optimal policy, or what is an exploration, what is a good exploration policy, which is, of course, it is in the literature, it is defined as a policy which can collect more reward along the way. And the way that we can also define reward is basically how much we approach a target. Okay, so it is based on the utility of each cube or subset of data, and how much this cube that we are currently investigating on relates to a target cube that we are seeking. And basically with that, we can define the notion of reward. And of course, then the problem of finding optimal policy reduces to the one to maximize the discounted cumulative reward. Now to do that, we have this, we propose this general solution, let's say, where, as we said before, we have this offline phase and this online phase. In offline phase, what happens is that now, instead of a human agent or a human user to explore different cubes with different exploration actions, we ask an AI agent to go and randomly for thousands to millions times interact with data cubes and collect rewards. And once we have this information, we can form and update a policy. Now, imagine that we have this policy, which is nothing but a mapper between states and actions. Now we are able to recommend actions in an online phase to the user, and the user provides feedback, and then this iterative process goes on. So basically, in this new architecture that we still have those feedback and guidance arrows, but now the guidance looks more smarter, and the guidance can recommend actions. The user is free to receive that recommendation or reject that recommendation, but the policy is assumed to be to be optimal, so that even if the current recommendation is rejected, later on the policy should um, compensate and come up with better actions in the future. Okay, so I won't go into the details of that. Basically, we know they are just typical reinforcement learning equations. We know that for optimizing policy, one easy solution is to optimize the value function for that learning system, and the value function is simply how much reward do we get by starting from a state and going until the target. Something that I want to focus as my last point in this part of the talk is that, well, if we look more precisely here, we see that the way that we define states, we can have millions of different states, because each given input cube and each given output cube can form a state. And then learning on top of these states should not be that much ideal, or basically it should be a sparse learning, which wouldn't be generalizable that much. So as a common practice done in reinforcement learning, we also applied this notion of feature functions. So instead of using the raw states, as we said before, we try to characterize each state with some features, such as, for example, how much diversity um, uh, this state has, how much coverage it has, how much size it has, or different kinds of things. And then we enforce our system to not only learn the interactions between state and actions, but learn the interaction between actions and the features of those states. And this is a simple stochastic gradient descent by the minimization of mean squared error to obtain the optimized policy. So this is an example of an exploration policy which is learned. For example, again, I am in the example of forming a program committee. So I see that, for example, the first cube, the first guidance, contains some groups of researchers, and then the agent decides to pick this group, including female researchers in Europe. And then you see that there are different features describing the state. And then we have different exploration actions which get a value for each of these features. So for the next step, the agent will choose the exploration actions which with the highest reward from all these features. And this is how the AI agent is able to go on and go on. And basically, you see it starts discovering program committee members more and more. First, it was 0 at the beginning, and then it becomes 2, 1, and then it goes on and collects more program committee members. Another experiment that I want to share with you here is that how much effect does it have if the target is spread in more cubes or just in single one cube. And it is somehow obvious that the number of steps that we need if the spread is more is more. So when the target is, let's say, more subjective, or it's spread through different cubes or different parts of the data, we need more time, we need more sessions to reach to the target. And the last point that I also have here is that the potentials of transfer learning here. We also, try to learn a policy on one program committee and try to adapt that for forming another program committee. For example, in this case, WebDB workshop and Sigmod. And we observe that, interestingly, it is possible. And different conferences, different tasks, although they are different, but because they have commonalities, they can have some improvements in transfer learning. So I want to conclude here, and then we can discuss about these two lines about formalizing and learning interactions later. But anyway, in the conclusions, what I try to say here is that human in the loop data analytics is a must to consider in today's machine learning applications, because if the user is outside the loop, we won't have personalization, we won't have customization, and we won't have transparency. And then what I try to show is some models where users and AI system can cooperate to reach a common goal. And we found that reinforcement learning is a good infrastructure to host these models. And last, I also mentioned the potentials of transfer learning, which could be an option here. These are my collaborators about the works that I mentioned today, and I thank all of them. And if there are any questions, I'm happy to answer them.
Oh, thank you, Beros, for this very, very interesting presentation and talk. And I think that participants here, I'm sure that they will have some questions. So I see that the first question on the discussion is, what is the used algorithm to learn users' interactions? Is the data set available?
Well, uh, two questions, and both are good. The first one is that, as I mentioned, but I was very fast on those slides. So it is we use reinforcement learning structure to use that, and more specifically, we use Q-learning, um, an updated version of that, which is SARSA. Um, Recently, deep reinforcement learning has taken over, and we could also use that. But at the time, we tried to also keep policies simpler and more transparent. And so later, we can also adapt deep reinforcement learning. Regarding the data set, as we said before, we assume, and it's somehow a realistic assumption, that exploration logs don't exist. And if they do, they are very specific to one domain, either visualization or data cleaning or things like that. So what we did is that we asked our agent to simulate those logs by navigating the data cubes thousands and thousands of times. so that we produce those logs and then we start learning from them.
Okay, thank you. Before announcing the next question, you have two comments. Nice talk, bravissimo Boris, very vibrant talk
Thank you.
from Nadia and Genoveva. And the next question is from Nadia. What about the time effect that could be expected from the user and loop learning mechanism?
That's also a very good question, and efficiency is one concern when we talk about human the loop data analytics, and this is where I guess database techniques are more prominent. So what we did for capturing efficiency was that um, the way that we formalize each exploration action, as we discussed before, which they should satisfy some local constraints and one global constraint, which is an optimization problem. um, we try to solve the bottleneck of this, which is that optimization. And to solve this bottleneck, we had two solutions which are simple solutions in the state of the art. One was using a greedy algorithm on top of an index, an inverted index that we built offline. I didn't talk about these details in the talk, but what we do is that behind the scenes in an offline process, we capture the similarities between each single pairs of data cubes. So once we have this information, and we also rank them, so we have these inverse lists of how the relevance looks like between each pair of data cubes. So when we want to optimize either diversity or coverage or any other objective online, we can do it relatively fast. And we also consider a time limit parameter for our algorithm, so that we respect that time limit parameter with a greedy algorithm. This way we can at least guarantee some efficiency in this interactive context.
Okay, thank you. Other questions?
Yes, I have a question.
Sure,
Thank you, Berus, for having
sure.
accepted first. Um, I was at some point in your presentation, I was wondering about how to be close to a target person, but the thing is that a target has many different perspectives of the way she wants to be recommended depending on different situations. So if I'm in my scientist, under my scientist identity, I might need some recommendation different than when I am a civilian. And then you came up with these policies, how to deal with having different policies for one user, but then how to activate one of the policies depending on the situation. How could you, how could we do that, and how could we learn how to do it?
Yes, 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 that's an excellent question, and basically the question belongs to our future work. But I try to elaborate on that. And it's a very interesting question. So the assumption here with the actual work that I presented today is very simplistic, which means that we have a policy which is applicable everywhere, which is not realistic. But let's first do that. But then the next step, as you mentioned, is that first now we need to have policies um, as a function of different situations, different roles, different needs, and all those sorts of things. And in this case, what we are trying to investigate is to consider these kind of learning interactions, but several of them working in parallel. So now instead of having just one single AI agent interacting with the data, we have several of them, and each of them has a specific task. One is going to imitate a data scientist, and the other one is going to imitate an information consumer, or things like this. And then once we have all these learned policies, now we have a bag of policies. Now what we can do is that, first of all, we have specific policies for each case. On the other hand, we can also have a distilled policy, or a policy which captures all commonalities with all other policies. So now in this case, we can first have some sort of a decision maker between policies, that common policy, that distilled policy, which can say that, okay, here's what you have to do in general, and then I can address you to more special policies, and then it can go on. So basically, it makes a two-layer mapping function instead of just a single mapping function, and this is something that we are currently working on. Thank you for the question.
Thank you.
Thank you. I have one question, but in continuity, I think. As you know, moreover, the different situation, etc., you have a diversity of the domains, so you cannot treat the same thing for instance, for the conferences or for the healthcare domain, etc. So I think that the domains are not are very different, and the queries are not the same. So, do you think that we can go through a hybrid approach using neural revolution algorithms behind the machine learning, just simple or maybe tiny machine learning using that? And do you think that we can go also through explainable artificial intelligence behind?
There are two very good questions. So about the first one, of course, there are two answers here. One answer can address the beginning of the pipeline of learning, and the other one, the end. So the way that we try to tackle the challenge that you mentioned, which is different domains and generalizability, specialization, and these questions, was that we thought that what if we design our exploration actions in a generic way, so that they are not really dependent on any domain themselves. They can be, for example, as you observed, I always mention the term data cubes, which could be everywhere. It could be a cohort of patients, or it could be a group of researchers, or it could be a sportive team, for example. So, and then all those exploration actions, we try to make them generic enough so that they are applicable to all domains. Now the question is that, okay, we have these exploration actions, we have the AI agent who can pick any of these exploration actions and apply them on the data. So let's the AI agent do that, collect a set of logs, and learn a policy for that specific domain, right? So we try to basically make our lower level architecture generic enough so that it can capture more complex domains at the end. But the other question that we also tried to answer with this transfer learning notion was that if there exists some commonality between some tasks, although they seem different, it seems that transfer learning in policies could help. So it's not necessary, for example, consider search and recommendation. They are not really two different domains, but they are two different tasks. But it turns out that if we know how a sequence of searches work, we can adapt them to a sequence of recommendations, and we can also improve the quality of recommendations or something like that. The other question about explainability, it is very important, and even before the notion of policies, because we have users in the loop, it is important for the user to know what is happening
Yes.
and how should I react to these notions. And it is an ongoing discussion for ourselves. We are not really sure how this explainability should be captured. It is a challenging question, and there are different methods, whether we have to consider explainability at each single level of the process, or we should either only look at the end of the process. But again, as an initial effort that we tried to do in this work was to come up with policies which are explainable in terms of the features. In this slide that I showed uh, before, which was here, right? So here, at least I can say it's not a perfect explainability, or as people say, interpretability, but at least I can say that why the agent chose by distribution exploration in this case. The reason is that based on all these features that I use, if you sum up the weights that they got, it gets the highest weight.
Mm.
So again, a very simplistic way, for example, with DQN or deep reinforcement learning, coming up with these weights in this clear way is a bit tricky. So by using, for example, non-deep approaches such as Q-learning in this case, we try to reach this explainability, but there is a long way to achieve explainability, and there is too much work to do with
There is a
this.
lot to do, I think.
Absolutely, absolutely. Yes,
So,
yes.
other questions? Let's see. So maybe we can. Thank you very much, Veros, for this nice talk. And I think that you reached us, all of us, with all those questions and the different issues that are discussed in your lecture, talk.